or lighter molecules will travel faster. Okay, and then another phenomenon is what we call effusion. Now, effusion is the process where you have a container of gases with certain amount of pressure in there, and you have a vacuum next to it. Now, if you poke a very small hole on the barrier, on the separation there, the gas molecules will be able to go through those small openings. Eventually, the pressure on both sides will equalize. So this is before effusion, you have hydrogen gas on one side, and this side is vacuum. You have small holes on the partition. Okay, and then if you give it long enough time, hydrogen gas, nitrogen gas will be able to go through that porous barrier. Eventually, the volume on both sides, the pressure on both sides will equalize. And so that's the effusion process. Now, effusion process also has something to do, or how fast they're moving, also has something to do with the molar mass of the molecules that we're dealing with. Okay, and this is what we call the Graham's equation, governing the rate of effusion. And again, this particular equation, we don't need you to memorize the equation. You will see homework questions related to this particular topic, but we don't need you to memorize the equation. I am not going to test you in the exam about this particular topic there. So here, it basically says the rate of diffusion of a gas is inversely proportional to the square root of the molar mass. In your textbook, there's a fairly detailed derivation of this particular equation. How do we come up with this particular equation there? And that's something that when you read the textbook there, that's something that I do want you to pay attention to, but it's not required for the upcoming exam on Tuesday. Okay, so this is the equation that governs the diffusion process, and basically, this equation implies caviar gas will move at a slower pace than the lighter gas in terms of molar mass there. So it has something to do with the molar mass, but it's not a direct relationship to the molar mass, rather it's the square root of the molar mass there. Yeah. So using this equation, this is a calculation that we can ask you to do, a type of question that we can ask you. If you have an unknown gas that effuses at a rate that is 0.468 times the rate of oxygen, what's the molar mass of this compound? Well, how do you analyze this equation, this particular process? So rate of the unknown gas equals to 0.468, the rate of oxygen. So that's what the question is telling you. Okay? So using the equation that we introduced on the previous slides here, the rate of unknown gas divided by the rate of oxygen would be 1 over 0.468. Okay? So that should equal to, well, they're inversely proportional to the square root of their molar mass. So in this case, oxygen gas goes to top, so 32 grams per mole, and then the unknown gas, X. Okay. So here, X is your only unknown. And you plug in the unknown, you plug in the equation, plug in the numbers there, and solve for the unknown. Square on both sides, and then cross multiplication. You solve the answer, you solve for the problem there, you end up with 1 or 26. So that's how you set up the equation there. And again, you will see similar type of questions in your homework assignments there. And that's something that I want you to have a chance to practice, but I will not test you on this particular topic in the upcoming exam on Tuesday. So make sure when you're working on a homework assignment there, make sure you do these problems. If you cannot figure out how to answer these questions there's a section in the textbook there actually talk about the Graham's law, the relationship between the rate of diffusion versus the molar mass. So make sure you read the textbook there and then try to answer the questions there. If you can't, I wouldn't mind if you skip this part in terms of preparing for the upcoming exam there. If you want to skip this part for now, you can definitely do so. Okay, so that's our learning object number 5 there. We're dealing with, based on the postulation there, based on the kinetic molecular theory, we are dealing with the motion of the gases. There are different types of gases. What's the relationship between how fast they move versus how heavy they are. And our last topic in chapter 5, we're going to looking back, based on all of the assumptions that we made, we're going to look back and see whether or not those assumptions are valid. Remember the ideal gas assumption. We have a list of 6 things. Number 6 is that there is no interaction between the molecules of gases, and there's no attraction and repulsion between the particles there. So we need to take a closer look at those assumptions, and under what conditions those assumptions are no longer valid, and we need to make corrections there. Okay, so the real gas versus ideal gas, really in the real gases we're dealing with gas particles, they do have volume, no matter how minor, how small they are, they do occupy volume. Okay? The ideal gas, they have mass, they don't occupy volume, so their size are negligible. And so in this case, ideal gas law would work well with real gas under low pressure, somewhere around 1 atm, 1 to 5 atm. That's a normal pressure there. You know, when you go scuba diving there, 20 meters and 60 feet into the water there, you can still handle that kind of pressure. And we consider that as a low pressure. So anywhere around 1 to 5 atm, that's a low pressure. High temperature, room temperature. So using ideal gas law, working on regular gas, real gases, it works well when you have low pressure, when you have high temperature there. Okay? Now, the ideal gas law assumes the gas molecules have no volume. There is no what we call intermolecular forces there. There's no interaction between the particles of the gas molecules there. Okay? Now, these assumptions are no longer valid if the conditions are changed. So the deviation from the ideal gas law, they're real gas particles, first of all, they do have volume, no matter how small volumes are for each particle. And if you have a large collection of gas particles there, you put them into a container. A container has a volume. The volume of the container does not equal to the volume of gas. The volume of gas really is the volume of the container minus the volume of each gas molecule occupies there. So that's the problem with the ideal gas law assumption. When they are far apart from one another, and they're low pressure, molecules are far apart from one another, we can neglect the volume of the gas there. But if you generate a condition where the molecules are pushed much closer to one another, then that assumption, you will have problems with that assumption. Okay? And real gas particles do interact with what we call intermolecular forces. If they are far apart from one another, interaction may not be strong enough to exhibit a result. However, if you have very high pressure, you push the molecules very close to one another, well, they are going to interact with one another. That's going to interfere with the pressure observed in the laboratory there. So real particles, real gas particles, they do interact with one another through intermolecular forces there. So at high pressure and low temperature, these factors become significant. Then if you look at the molar volume of the gases there, we say under normal condition, low pressure, high temperature there, is that any gas under STP will take 22.4 liter of space. Well, that's the ideal gas assumption. And if you look at the real gases there, chlorine, 22.06. Not a huge difference there, 22.4 versus 22.1. Okay, and carbon dioxide, 22.31, and ammonia, 22.4.